on leave today, so I'll be taking your classes. Okay, so I will take these. So today and maybe on the next class, I will be taking it. Huh? So, what was Bali doing in the last class? What you did in the last class? Electric field lines?
Electric dipole in uniform electric field.
Okay, so you did electric dipole in uniform electric field. Fine. And you have finished your electric field lines already?
Yes,
Mazia. So you have finished electric field lines. Fine. So did you did that electric dipole in non-uniform electric field, or you just did in uniform field only? Yes, you did only uniform field or non-uniform field also?
Only uniform.
Only uniform field. Okay. Okay. Tell me, Mazia. So what happened if I place an electric dipole in a uniform field? What's the net force on the dipole in uniform field? Mazia. What happened if I place a dipole in a uniform field? What's the net force on the dipole? You can check your notes. Minashi, what's the net force on the dipole if I place that dipole in uniform field?
0.
0. Very good. And 0 force means the dipole should remain at rest. So it will remain at rest, or it will experience something else?
It's at rest.
No. That dipole will experience a torque, right? And due to that torque, this dipole will try to rotate. So when you place a dipole in uniform field, the net force on the dipole is 0. 0. But your dipole will experience a torque, and that torque is given by this expression, P cross E. Maharaj, I'm putting you in waiting room for just 2 minutes. Huh? I'm just putting you in waiting room for 2 minutes. Maharaj.
Okay, sir. Okay.
Okay, so net force is 0, but a torque will act on the dipole, and that torque is given by P cross E. Mazia, what happens if torque act on the dipole? The dipole will remain at rest, or it will have some type of motion? Mazia, what happens if I put a dipole in a uniform field? It will experience a torque. Due to that torque, what will happen with the dipole? It will remain at rest or will have some type of motion? Yes, motion. What type of motion, Mazia? Mazia, it would be better if you use your mic. Huh? Yeah, what type of motion, Mazia? It will be a straight line motion or rotation? Hishma, your physics teacher Balinder sir is on leave today, so I'm taking his class. I will continue the topic where he left. Yes, it will rotate. Fine. So this is what you did in the last class. The next topic is electric flux. The next is electric flux. See, in chapter number 1, the topic that have the maximum weightage is electric flux. In all boards as well as in your entrance exams, the maximum weightage of any topic in chapter number 1 is that of electric flux. So see, what does electric flux means? Electric flux means that electric flux is the number of electric field lines, electric field lines crossing an area normal. Crossing an area normal. So the number of field lines crossing an area normally is known as electric flux. So if I draw this area and I say that 3 field lines are crossing this area normally, then the flux will be equal to 3. This is how we represent flux. We represent flux by phi. So flux is just the number of field lines crossing an area normally, that is electric flux. There's another way to calculate this flux, and that is, if you have an area, the next method is to calculate area vector. See, in general, area is a scalar quantity. But when we calculate flux, we provide a direction to area. We make area as a vector. So we consider area as a vector when we study electric flux. So to make area vector, we have to provide a direction to the area. So the direction of area is perpendicular to the area. The direction of area vector is perpendicular to the area. Direction of area vector is perpendicular to area. This is the direction of area vector. That's the direction of area vector. Sefula, your physics teacher Balinder sir is not available today, so I'll be taking his class. Huh? We are continuing only that topic which he left. He was supposed to start electric flux, so started that topic only.
Okay, sir.
So area vector is, direction of area vector is perpendicular to the area. So if I take this hand as the area, then the direction of this is perpendicular to it. That's the direction of area vector. So if I take xy plane, my area is in xy plane. Yashika, what's the direction of xy plane? Yashika, what is the direction of xy plane? If my area is in xy plane, then what's the direction? Yashika is not in class, huh? Mazia?
I cap.
I cap? Why I caps? The direction perpendicular to xy plane cannot be I cap. Mazia, try. What's the direction? Which axis is perpendicular to xy plane? Okay. Minashi, which direction is perpendicular to xy plane?
Is it Z?
Z. Mazia, y is in xy plane. It can't be perpendicular. See, look at this mobile phone. This mobile phone is in xy plane. Huh? The plane of your board, the plane of your copy on which you are writing is in xy plane. This is xy plane. So if I want perpendicular over this xy plane, then this is the perpendicular. Huh? This is y axis, this is x axis, and which axis this would be? Hishma, this will be x, y, or this will be z?
Z axis.
Z axis. Huh? So the axis which is perpendicular to xy plane is the z axis. Is z axis. Huh? It is the z axis which is perpendicular to xy plane. Similarly, if I asked you the direction of yz plane, the direction of yz plane is, Saifullah, can you guess now what should be the direction of yz plane? Which direction is perpendicular to yz plane?
X-axis.
X-axis, great. Similarly, if I ask you the direction of xz plane, the direction of xz plane will be y-axis. So to calculate flux, first of all, we provide direction to area, and the direction to area is perpendicular to area. Or I should write this as outwards normal. This is area vector. Next. Now we know area vector. Now see how we define flux. So this is an area. And this is the direction of area. Perpendicular to the area, it's n cap. That's the direction of area vector. And this is the electric field. The angle between electric field and area vector is theta. This is the angle between electric field and area vector. So I can write that electric flux, which is the dot product of electric field and area vector. This is how we define flux. Area is S. So this S vector is S into n cap is the area vector. That's the direction of area vector. So this is the direction E dot is. And how we open this dot product? Noha, what is E dot S? How will you open this dot product?
So ES cos.
ES cos theta. Now, for the purpose of numerical, this angle theta is important. See, what is theta? Theta is angle between electric field and area vector. It's not the angle between field and area. It's the angle between field and area vector. So theta is the angle between electric field E and area vector. Now, what's the direction of area vector? It's perpendicular to area. So basically, this theta is the angle between electric field and perpendicular to the area. See, the plane of area is this. If I show you using my mobile phone, say this is the plane of area. So if let's say this is the direction of electric field. I guess this is visible now. This angle is the angle between electric field and plane of area. This angle is the angle between electric field and plane of area. We are not taking this angle. We need angle between perpendicular to the area. I have anything else? Yes, I have this. This is the area vector. I need angle between this area vector and this electric field. That is theta. So when we calculate flux, we don't take angle between electric field and the plane of area. What we take is the angle between electric field and normal to the area. So what type of quantity this flux should be? It should be a scalar or a vector quantity, Hishma? What type of quantity this flux should be? Should be a scalar quantity or it should be a vector quantity? Hishma.
Vector.
See, the quantity which we get after dot product is always a scalar. Okay, dot product gives scalar quantities, cross product gives vector quantities. So it's a scalar. Now, if I write the SI unit of this quantity, so the SI unit is its electric field, which is Newton per coulomb, multiplied by area, which is meter square. So that's Newton meter square per coulomb. Or I can write this in terms of volt also. So this is volt per meter into meter square. So I can write this as volt meter now. This is the direction. SI unit is volt meter. Next quantity. Let's take a very simple question just to clarify this formula. This is an area. Let's say the area is 2 meters square. This should be the direction of this area. This is your field. Let's say your field is some 5 Newton per coulomb. And this angle is, this is the 60-degree angle. So I'm writing the language. Electric field of 5 Newton per coulomb exists in space. Calculate flux through area of 2 meters square if field lines are inclined at 60-degree with plane of area. 60-degree with the plane of area. So I will be using this expression. Phi is ES cos theta. So E is 5, area is 2. What is theta? Unib. What's the value of theta?
So 60 degree.
60 degree. Mazia, it would be 60.
Yes.
Yes. Minashi? Will it be 60 only?
Yes, sir.
Yes. Yashika,
Sir, 30 degree.
30 degrees. See, when I wrote this formula, I have mentioned that theta is angle between electric field and area vector n cap. This is the angle theta, not this one. See, this is not your angle. This should be your angle theta. So Minashi, what would be the value of theta?
30.
30. Yes, we don't take angle theta with the plane. We take angle theta with the normal. So that will be 30-degree angle. Is it clear? Everyone else? Mazia, Unib?
Yes, sir.
We take angle with the normal, not with the plane. So that's 30 degree. I put cos 30. So that is 10 into cos 30, which is root 3 by 2. 2 5s are 10. So that gives you 5 root 3 voltmeter. So that's your choice. You write voltmeter or you write Newton meter square per coulomb. That's the simplest type of question. The second type of question is in Cartesian form. So I have an electric field E, which is I cap plus 2j cap plus 3k cap. Then I have my area vector. It's 2I cap plus 3j cap minus 4k cap. It's meter square and it's volt per meter. I need flux. Saifullah, how will you calculate flux? I need flux through this area. Electric field is given and area vector is given. How to calculate flux?
E vector dot product of E vector and S product. S vector.
E vector and dot product of S vector. Very good. So what is E vector? It's I cap plus 2j cap plus 3k cap. Dot is H vector, which is 2I cap plus 3j cap minus 4k cap. How to take the dot product, Saifullah? What will the final result of the dot product? Okay. Hishma, what will be the final result of dot product? Noha? Noha, final result of the dot product.
So 2 into 1 plus 3 into 2 plus 3 into minus 4.
So yes, when vectors are given in Cartesian form, to take dot product, what we do is we multiply the coefficient. The coefficient of I cap is 1 and coefficient of I cap is 2. So first of all, I will multiply 1 into coefficient of j cap is 2, coefficient of j cap is 3, then multiply 2 into 3. Coefficient of k cap is 3, coefficient of k cap is minus 4. So I will multiply 3 and minus 4. So this will be, is it clear everyone how to take dot product in Cartesian form? See, in Cartesian form means I cap, j cap, k cap. When the vectors are given in this form, in the form of I cap, j cap and k cap, then you don't need angle between vectors. You don't need an angle between E and S. You just multiply the coefficients, like you multiply the coefficient of I cap with the coefficient of I cap, coefficient of j cap with the coefficient of j cap, and k cap with the k cap. So that's 2 plus 6 minus 12. It's minus of 8 voltmeter. Mazia, clear? Okay, one last question. Electric field is this. I cap plus 2j cap plus 3k cap volt per meter. Calculate electric flux through area of 3 meters square in XY plane. First, note down the theory, then start doing this numerical. A bit, note it down. We started electric flux. Electric flux is just the number of electric field lines crossing an area normally. So if I take an area and 3 field lines are crossing this area normally, so flux will be 3. So there are 2 methods to calculate flux. The first is you can calculate flux just by counting the number of field lines, or you can calculate flux by the dot product of electric field and area vector, ES cos theta. So to make area a vector, we provide a direction to area, and the direction is perpendicular to the plane. So if I take this area, my hand is the area, I want to provide a direction to this area. So direction of this area will be the perpendicular to my hand. This is the direction of area vector. Note it down.
फिर उसके बाद यहीं से कराया था ना कंटिन्यू।
हाँ क्या अर्पित?
मैं पूछ रहा था उसके बाद आपने यहीं से कंटिन्यू कराया।
हाँ यहीं से।
Sir, please scroll.
Tell me if you have doubt in any topic. Arpit, issue koi?
No, sir. सर ये नीचे वाला क्रॉस प्रोडक्ट वाला समझा।
कौन सा वाला? This one?
ये सर जो नीचे आपने डायग्राम बनाया हुआ है।
Okay. See, this cross. This is your area S. This is the direction of area vector n cap. The angle between electric field and area vector is theta. This is the angle between electric field and area vector. We define flux as the dot product of electric field and area vector, E dot S, which is ES cos theta now. This is how we define electric flux, the dot product of electric field and area vector.
Okay.
Yes, can I scroll it further?
So can you scroll up for a second?
Yes. Safula, any doubt?
No, sir.
Ishma, are you getting it?
Well done.
Okay. Now, solve this question. Answers.
सर इसका जो आंसर होगा वो -4 होगा ना?
Okay, Minashi. No, Minashi, you're wrong. Noha is correct.
No, sir, the first one I said.
Okay, the first
Yeah.
one. It's minus
First one.
8. Yes,
Four.
-4. Right. Minus. For the second one, Noha is correct. Unib wrong. Unib, क्या बोला था?
सर मैं यही बोल रहा था कि उसका -4 होगा.
अच्छा, मुझे लगा second.
सर एक चीज पूछनी थी. सर अगर ऊपर वाले क्वेश्चन में डॉट प्रोडक्ट की जगह क्रॉस होता तो फिर कैसे निकालते हैं?
फ्लक्स क्रॉस से नहीं आएगा. For
नहीं
flux,
सर,
you need
मतलब
dot
मैं
product.
वैसे पूछ रहा हूँ कि अगर
Okay, okay.
क्रॉस कैसे निकालता मैं ये?
Determinant. Just open this determinant. Huh? Expand this determinant by the first row. That's it. You know how to open a determinant. Huh?
Yes sir.
Let's just open this determinant. First row is I cap, J cap, K cap. Second is 1, 2, 3. Third is 2, 3, minus 4. Just open this determinant from the first row. That will give you the result of the cross product. Yes, Yashika is correct. What about the rest? Mazia, answer. Hishma. Hishma, are you in class?
Yes, sir.
Okay, so what's your answer? Nothing.
It's
Huh?
some
Saifullah, your answer? C. Your electric field is I cap plus 2J cap plus 3K cap. Yes, Noah and Yashika are correct. See, your area is 3 meters square in XY plane. So if your area is in XY plane, then what is the direction of area, Hishma? Hishma, if your area is in XY plane, then what is the direction? Yes, Saifullah, you are correct. The direction of area is perpendicular to the plane. Mazia, which axis is perpendicular to XY plane? Z. And what's the unit vector along Z axis, Mazia? What is the unit vector along Z axis? Very good. K cap. Huh? So you can write this as this is 0 I cap, 0 J cap, 3 K cap. So for flux, you can take dot product of electric field and area vector. The coefficient of I cap is 1, coefficient of I cap is 0, so that is 0. Coefficient of J cap is 2, coefficient of J cap is 0, so it's 0. Coefficient of K cap is 3, coefficient of K cap is 3, so that's 3 into 3, so that is equal to 9 voltmeter. So this is the direction of area vector. This is a flux. So whenever you have area in this form and electric field in Cartesian form means in the terms of I cap, J cap and K cap. So provide a direction to your area. So if your area is XY plane, that means its direction is along Z axis. So give it a direction of Z axis. So that will be 0 I cap, 0 J cap, 3 K cap. So that is 9 voltmeter. Is it clear, everyone?
yes, sir.
Okay, just note
Yes,
it
sir.
down. Then we'll see how to calculate flux for a curved surface. This is easy. Like if you have plane surface, then this is easy. See, we can classify your surfaces into two categories. You can have two types of surfaces. You can have a plane surface or you can have a curved surface. The example of plane surface is square. Square is a plane surface. Huh? Disk is a plane surface. On the other hand, curved surface is sphere. It's curved. Cylinder is an example of curved surface. See, in plane surfaces, the direction of area vector does not change. The direction of area vector remains same. Like if I take this plane surface, this is a plane surface. The direction of area of this plane surface is fixed. It will not change. This is the direction of area vector here, 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 here. The direction of area vector is not changing for this particular plane surface. But if you have a curved surface, like if I give you some sort of cylinder, let's say this is a curved surface. The direction of area vector over curved surface will change. Here, the direction of area vector is towards you. But for this end, the direction of area vector will change. Here, the direction of area vector will change. So if you take a curved surface, then over a curved surface from point to point, the direction of area vector will change.
Excuse me, sir.
Yes.
Sir, but you took the third surface in 3 dimensions.
Even if you take a curved surface in 2 dimensions, like if you consider just this much of portion of this curved surface, take this small portion only, then again it will have different area vector, right? Over this point, area vector will be different. Here, area vector will be different. Here, area vector will be different. So that is the difference between the plane surface and the curved surface. So here, direction of area vector is constant. Direction of area vector is constant. Area vector is constant. And if you take a curved surface, then from one point to another of curved surface, direction of area vector will change. Direction of area vector will change. So direction of area vector will keep on changing if you have a curved surface, but it will remain constant if you have a plane surface. That's one thing. Another thing is you can have two types of electric fields. You can have a uniform field, or you can have a non-uniform field. So when we say that field is uniform, uniform field means both magnitude and direction of field does not change with time. So if you have a uniform field, then both its magnitude and direction will not change with time. But if you have a non-uniform field, then magnitudes or direction or both can change. So it's have almost the same definition, just like your what do we say, uniform and non-uniform velocity. And it's not with time, it's with position. So we have these two types of surfaces, plane and curved surfaces, and two types of field, uniform and non-uniform field. Now, this relation phi is E dot ds is valid only for plane surface plus uniform field. So if you have a surface which is plane and a field which is uniform, then you will use this expression. E dot, sorry, not ds, E dot s. The expression that we use in the previous three numericals. In all these cases, your surface is plane, your field is uniform. But if you have a non-uniform field, or if you have a curved surface, then your phi will be its integral of E dot ds. This we use if we have a curved surface or non-uniform field. So if you have a non-uniform field or if you have a curved surface, so for that particular combination, you use this expression E dot ds. And there is one more case. If your surface is closed, if surface is closed, for example, you have a sphere, it's a closed surface. So in a closed surface, what we can do is we can put an integral, this closed sign over the integral. This closed sign says that the given surface is closed. So whenever you have numericals of electric flux, first of all, try to classify whether the surface is plane or the surface is curved, and then take your field, whether your field is uniform or your field is non-uniform. If your field is uniform and your surface is plane, then you can use this expression E dot s. Otherwise, if you have a curved surface or a non-uniform field or curved surface with a non-uniform field, then you will take the integral. You will calculate flux for a small area and then you will integrate it over the entire surface. Or if your curved surface is closed, then you can put a closed sign over this integral. See, you know how to integrate an expression, but it's not a normal integration. This is a surface integral. Surface integral. Usually surface integrals are not a part of school syllabus. So in this particular case, you don't have to solve the entire surface integral. You just have to memorize two relations and all your numericals will be related to those two expressions only of surface integral. First, note it down and tell me if you have doubts, any doubts.
Sir, can you please explain the concept of that closed sheet?
Where? Previous question?
So the last part you explained, like,
Last part.
yes.
This one.
Yes, sir, third part.
So we use this expression E dot S if your surface is plane and your field is uniform. For a plane surface and a uniform field, we can use this expression. Direct take the dot product of electric field and area vector. But if I give you a non-uniform field, or I ask you to calculate flux passing through the surface of a sphere or a cylinder, which is a curved surface. In case of curved surface, you can't use this expression directly. You need something else. You will need this integral of E dot S. And if this curved surface is closed, one good example is a sphere. Another example is cylinder with ends. If you cut the ends of the cylinder and it's not a closed surface, cylinder with ends, then you will use this circle. This circle means it's closed. This integral is not a normal integral that you did in class 11. It is a surface integral. To solve a surface integral, there are certain steps. One of the step is to solve the surface integral. Basically, the surface integral is not a part of school syllabus. So I won't teach how to solve a surface integral. For all numericals and all derivations, you will need just two expressions of surface integral. Just two expressions that those two expressions we'll discuss at the end. Arpit.
Yes, sir. So what is written after both?
Or both can change.
No,
No
sir,
need.
uniform.
Both magnitude and direction of field does not change with time.
Okay.
Can I scroll it?
1 minute, sir. Can you go up?
You're writing? Yes, Saifullah, written.
Yes, sir.
Yes, can I scroll it? Written. Okay, the next topic is surface integral. Now, to calculate Gauss law, you should know two surface integrals. One is on the surface of sphere. Like if I take a sphere, the radius of the sphere is r. I consider a small element of the surface of sphere. I call this a small area as ds. If I integrate this ds, Hishma, can I use closed integral here for sphere?
Yes.
Yes, sphere is a closed surface. So when I integrate it over the sphere, it comes out to be 4 pi r square. So this is one integral that you should remember. From here to here, there are several steps involved in integrating this ds and getting this 4 pi r square. But I'm not discussing those steps. Those steps are not a part of the syllabus. Second is cylinder. Not the entire cylinder, but just the curved surface. Just the curved surface of the cylinder. So if you take a cylinder, the radius of the cylinder is r, the length of the cylinder is L, and integrate it over the surface of cylinder, then that will give 2 pi r. This is surface integral. Integral of ds is 2 pi r. That is the surface integral. So this is surface integral over the sphere, and this is integral over a cylinder. I can't use closed here because I'm taking only the curved surface. I'm not considering the ends of the cylinder. So if I'm not considering the ends, that means it's an open cylinder. So I can't use a closed sign here. It's just integral of ds, which is 2 pi r. So these are the two integrals that we will use when we will calculate flux for curved surfaces. Just note it down. Written. Arpit, Minashi.
So written.
Yes, sir.
Okay. Let's solve first question on a curved surface. Huh? Yeah, going towards Gauss law. So the first question for curved surface is a charge q is placed.
Sir, it is which law?
It is Gauss
Which
law,
law is
Gauss law, Gauss law, Gauss law. GAUSS. A charge q is placed at the center of sphere of radius r. Calculate flux through the sphere. So you have a sphere. You place a charge q at the center of the sphere. The radius of the sphere is r. You're supposed to calculate the flux passing through the sphere. So which relation you will use, E dot S or integral of E dot ds? Yes, for this sphere, which relation you will use, E dot S you will use or integral of E dot ds?
Integral.
Integral of E dot ds, the curved surface. Huh? So what we will do, we will consider a small element. I call that small element as ds. What is the direction of area vector, Noah? This is a small area. What is the direction of this area? Noah. Unib, what is the direction of this area? Yashika, direction of this area? Array. Mazia, what's the direction of this ds area? Okay, open question now.
Towards the
Perpendicular.
tangent.
Outwards, huh?
Sorry,
Area vector
perpendicular.
is outwards only. And if I take electric field, then due to a point charge, electric field is also outwards. So what is angle between electric field and area vector?
180 degree.
180 degree. No. Two vectors are parallel. Angle is 0 degree. Yes. So when we calculate flux, we'll use closed integral of E dot ds. When I open this integral, this will be E ds cos 0. So I'm left with closed integral of E ds. What is the value of electric field at a distance r from the point charge, Minashi? What is the expression for electric field of a point charge? How much? Yes, 1 over 4 pi epsilon naught. Then
Q by R square.
Q by R square. So we can substitute this expression here. So when we do this substitution, we will get 1 over 4 pi epsilon naught. It's Q by R square into ds. So see, this 1 over 4 pi epsilon naught, Q by R square is constant. Q by R square is constant. We just have integral of ds. See, charge is constant. Radius of the sphere is not changing. This 4 pi epsilon naught is constant, and just ds. I'm left with ds integral. Noha, what is the integral of this ds? What's the value of integral of ds? Saifullah, what's the value of this integral of ds?
Sir, 4 pi r square.
4 pi r square. So this 4 pi will cancel this 4 pi, r square will cancel this r square, and you are left with q epsilon naught. So if you take a sphere, then flux passing through that sphere is q epsilon naught. See, there's one more thing. The result is independent of the shape and size of the sphere. There is no r term in this expression. Means this expression is independent of size of the sphere. This result is independent of shape and size of the sphere. Which means instead of this sphere, if I take something else, like if I take a cylinder instead of sphere, then also I will get the same result. Then also the flux will be q epsilon naught. Calculations may get tough, but you will get the same result. Not just cylinder. If you take closed surface of any arbitrary shape and you do the whole integral, this whole integral, then again you will get the same result. So this shows that this result is something special. The result is independent of the shape of the surface. The result is independent of the size of the surface. For the result, the only important thing is your surface should be a closed surface and you should have a charge inside the surface. And this particular result is a law in itself and is known as Gauss. one of the most important topic of your syllabus, Gauss. Is it clear, Yashika, Minashi?
Yes, sir.
Note it down. Then we'll do the statement of Gauss. Note it down. Noah, are you in class?
Yes, sir.
Okay.
Sir, please zoom out.
Mhm. Okay.
Yes, sir.
You can call this calculation as the derivation of Gauss law also. Although it's not the exact derivation of Gauss law, but you can call it as the
Can you
derivation.
repeat what did you say? Sir? Can you repeat?
Yes. I'm saying although this is not the exact derivation of Gauss law, but you can consider if in your exams someone asks you to derive Gauss law, then you can use this calculation. You can consider it as the derivation of Gauss law.
Excuse me, sir.
Yes.
So
Arvind.
why are you putting the closed integral on the both sides of the RHS?
No, it's not the closed integral, it's the sign of the flux. Huh? This is the sign of the flux. Okay, and this is the integral.
Okay.
Yes, sir. Can you speak soul?
Yes, written. Okay, the next thing is, if you have written this, now let's start with the Gauss law. See, in boards exam, the weightage of Gauss law is 3 marks. You will always get a question of 3 marks from the Gauss law. In your NEET exam, you will get at least one question, and similarly in J, you will get at least one question from Gauss law. Something very, very important. So see, what is the statement of Gauss law? Gauss law says if you have a closed surface, flux through a closed surface is 1 by epsilon naught times the charge enclosed by the surface. So this is Gauss law, that flux passing through a closed surface is 1 by epsilon naught times the charge enclosed by the surface. So if I take a closed surface, I put some charge Q inside the closed surface. And if I ask you to calculate flux, then that is closed integral of E dot ds. That will be equal to Q by epsilon naught. This is Gauss law. Charge enclosed, the total flux passing through a closed surface is 1 by epsilon naught times the charge enclosed by the surface. See, to use Gauss law, 2 conditions are important. The first one is you should always have a closed surface. Gauss law is not valid for an open surface. It's valid only for a closed surface. The second thing is charge should be enclosed by the surface. Charge should be inside the closed surface, not outside the closed surface. So these 2 points are important to use a Gauss law. Now we have certain properties. Well, I'm writing them as properties, but these are basically 1 marker questions. So the first one is its flux is independent of shape and size of closed surface. So the electric flux through a closed surface is independent of the shape and size of the surface. So if you take a closed surface, I put a charge Q here, then the flux through the closed surface is just Q by epsilon. If I change the size of the closed surface, like if I take this size of the closed surface, earlier the radius is R, now the radius is 2R. Now, what will be the flux? Noha, value of flux now. Mirage,
So Q upon epsilon.
U upon epsilon. If I take surface of any other shape, like if I take a cylinder, Mazia, what is the flux now? Flux Mazia. Ishma, flux. If I, instead of sphere, I take a cylinder, huh? What's the flux?
Q by epsilon naught.
Q by epsilon. You can take surface of any shape and size. If it is closed, then your flux will be Q by epsilon on the first property. Second property. Inwards flux is positive. No, sorry. Inwards flux is negative and outwards is positive. So if flux is entering the closed surface, then it's negative. And your flux will be minus of Q by epsilon. And if flux is going out of the closed surface, then it's positive. plus Q by epsilon naught. Second property. Third one. Charge outside the closed surface. Charge outside the closed surface won't contribute to flux. So outside the closed surface, it won't contribute to flux. If you have a closed surface and I put charges outside the closed surface, like a charge Q1 here, a charge Q2 here, a charge Q3 here, no, Q2 here, Q3 here, and Q1 there. Miraj, which one will not contribute to flux?
Plus Q.
Plus Q1, right? This is
Q1
outside the
plus
closed
Q1.
surface. It will not contribute to
Yes,
flux.
sir. Yes.
So only Q2 and Q3 will contribute to flux. Okay. Next property. See, if field lines are crossing a closed surface, if field lines are crossing a closed surface, then flux is zero. Is zero. So if I take this closed surface and three field lines are crossing, crossing means they are first entering into the surface and then they are leaving the surface. They are first entering into the surface, then they are leaving the surface. They are first entering into the surface, then they are leaving the surface. Now I want to calculate flux. Now, how many field lines are entering? Three. So see, if you can remember, we started flux with this definition only. What is flux? The number of field lines crossing an area normally. So here, three field lines are entering. The flux is minus 3. Three field lines are leaving. So plus 3. So that will be equal to 0. So whenever you have a closed surface and field lines are crossing through it, then your flux will be 0. Fifth one. Okay. Charge will not contribute to flux. This is okay, fine. So if you have a dipole inside the closed surface, I put a dipole. Saifullah, what would be the flux if I put a dipole inside the closed surface? What will be the value of flux? 0. Great. Because the net charge is minus Q plus Q by epsilon naught, and that will be 0. So if you have a dipole inside a closed surface, then flux is always 0. So these are some basic properties for Gauss law. Just note it down. We'll do some numericals over it.
Sir, please scroll.
Scroll up.
Yes, sir. Sir, please scroll. Sir.
1 minute, sir. Please go up. Done, sir.
Yes, Arpit. Okay, one last question and then we will end this class. You have a cube. So it's a cube. I place a charge q at the center of the cube. Charge q is placed at the center of cube. Calculate first part. Flux through cube. Second part. Flux through each face. So for calculating flux through the cube, you simply use Gauss law. Gauss law says that flux through the cube is just q by epsilon naught. So for each face, say cube have 6 faces. So if I say that flux passing through the cube is q by epsilon naught, that means flux through 6 faces is q by epsilon. Flux through 6 faces is q by epsilon. Flux through one face will be Q by 6 epsilon. Cube have 6 faces. If I'm saying flux passing through the cube is Q by epsilon naught, that means I'm saying that flux passing through 6 faces is Q by epsilon naught. So the flux passing through one face will be Q by 6 epsilon. Just note it down. Yes, can I scroll it further? Written, everyone? Minashi, Saifullah, written?
Yes, sir.
Okay.
Yes, sir.
Okay, so we'll stop here. The next class will continue with this thing. Huh? So let's stop here. Sure. Okay, thank you. Bye.
Thank you, sir.